Hey, laser enthusiasts! Welcome to my channel. Today, we've got an electrifying project in store for you. We'll be diving into the world of lasers as we build our very own transversely excited atmospheric, in other words TEA, nitrogen laser. I did this project as my independent physics project at Koç University with Professor Alper Kiraz and Serhat Naz from the company Optifil. So, let's break down the materials and tools for our TEA laser adventure. Starting off, we've got the powerhouse of our setup, the old TV flyback transformer, accompanied by its trusty driver circuit for generating that high-voltage magic. And to give this transformer a kick, we're juicing it up with some 10A batteries. Moving on to the heart of our laser setup, we've got not one, but two hexagon rods playing the role of the laser channel. These bad boys are ready to channel some serious electric energy. Now, for the capacitors, we've gone DIY with thin aluminium sheets. Yep, you heard it right, everyday aluminium is the key here. And for the dielectric material, we've repurposed old projector slides. Talk about recycling at its finest. And hey, check out this 1 mega ohm resistor doing its thing, connecting our capacitors like the unsung hero of the circuit. It's all about that smooth flow of energy. Last but not least, our base iron plate is holding it down as the ground to the entire circuit. It's like the foundation of our laser kingdom. So, there you have it, folks, the lineup of materials and tools for our TEA laser experiment. Stay tuned as we put all these pieces together and witness the magic unfold. TEA lasers, short for transverse electrical discharge in atmosphere lasers, are a captivating breed of coherent optical sources. Now, let's break down the science behind this fascinating phenomenon. In the thermal equilibrium of nitrogen, electrons predominantly reside at the ground level. However, in our setup, we shake things up by using electrical discharge to propel electrons to the uppermost laser level. The upper level, having a significantly shorter radiative lifetime than the lower one, tends to stay vacant. To keep the photon show going, we need to rapidly pump the electrons, ensuring the upper level stays charged longer than it discharges, a mere 40 nanoseconds. To bring this concept to life, we've crafted a pulse-forming network, PFN, circuit. Two capacitors, charged by a high-voltage source, unleash their stored energy through a spark gap, creating pulses as brief as 10 nanoseconds in the laser channel. This quick burst is ample time for individual nitrogen atoms to start emitting photons. Photons burst forth in all directions through spontaneous emission. Yet, the space beyond the laser channel remains unexcited by the electric field, leaving electrons in nitrogen atoms outside the channel mostly at the ground level. As a consequence, photons emitted in these directions get absorbed by nitrogen electrons on their journey to the upper energy levels. However, the game changes when photons travel in the direction of the laser channel. Here, they encounter nitrogen electrons at higher energy levels, prompting the release of more photons through stimulated emission. The induced photons boast the same frequency and phase as the incident ones, leading to optical amplification along the laser channel's length. And there you have it, the intricate dance of electrons, photons, and energy levels that culminate in the mesmerizing phenomenon of TEA laser lasing. Now, the moment we've all been waiting for, let's fire up our TEA laser and see it in action. Watch as the UV laser beam illuminates objects with different firing rates and pulse widths. So, here's the scoop on our journey to harness the brilliance of an ultraviolet, UV, laser from our setup. Brace yourselves for some exciting details. We successfully coaxed our setup into yielding a UV laser with firing rates of 5 Hz and 10 Hz, depending on the currents driving the power source. At its zenith, the laser exhibited a pulse width of about 10 nanoseconds. Interestingly, our simulations hinted at a firing rate of 20 Hz with unlimited input current, a result that aligned quite well with our real-world experimentation. To scrutinize the laser's performance, we employed a photodetector. Single-shot captures revealed interference and artifacts, so we opted for the maximum peak to characterize the laser's properties. The firing rate correlated precisely with the operating amperes of the voltage source. However, with only two power sources at 5.3A and 10A, establishing a solid linear correlation remained elusive. Single shots, while plagued by oscillations and interference, did not deter us. We persevered and chose the maximum peak as the laser pulse, characterizing its pulse width. The result? A 10 nanoseconds of laser pulse width at the highest peak. To complement our experimental findings, we delved into the virtual realm with a simulation using the Fallstad circuit simulator. This simulator proved ideal for our application, boasting built-in spark gap models, a feature conspicuously absent in other SPICE programs, where modeling spark gaps is a more complex affair. The Fallstad simulation mirrored our experimental results, showcasing a 20 Hz operation without current limitations and unveiling spark gap artifacts during the laser's single shot. The waveform closely resembled what we measured from the photodetector when aimed at the actual laser output. In summary, our endeavor led to the development of a TEA laser system that wielded the power to emit ultraviolet, UV, light, boasting firing rates of 5 Hz and 10 Hz. However, our journey was not without its challenges. Especially we had to try a few different setups for the laser channel electrodes until we settled with hexagon mills. We also needed to do quite a bit of sanding to smoothen sharp edges. The system only worked when we absolutely made sure that the electrodes are perfectly parallel and smooth. Single-shot measurements faced hurdles as interference issues surfaced. External electronics and environmental factors introduced artifacts, impacting the laser beam's purity. Despite these challenges, our collaboration with Serhat Naz proved invaluable, especially in designing the high-voltage source and leveraging simulation tools to quantify the electrical behavior of our system. The simulation results harmonized with the real-world characteristics, offering a robust validation of our setup. In essence, the successful realization of an atmospheric pressure nitrogen TUV laser marked a significant milestone in our understanding of TEA laser mechanisms. This project bestowed upon us not only theoretical knowledge but hands-on experience crucial for constructing similar ventures. The intricate details and specifications involved in bringing such a system to life became tangible, enhancing our comprehension of these complex ideas. Our TEA laser journey has not only illuminated UV light but has also illuminated our path toward future projects, fueled by newfound knowledge and the confidence to tackle intricate challenges. Stay tuned for more groundbreaking explorations in the world of lasers and beyond. Don't forget to like, share, and subscribe for the next chapter in our scientific adventures. Until then, keep pushing the boundaries of what's possible.